line spectra and the Bohr model. So the atomic emission spectra is also known as a line spectrum. And what it is a pattern of discrete lines of different wavelengths. Each element has its own particular line spectrum or atomic emission spectrum, which is characteristic of that particular element and can be used to identify the elements. So let's look at an example. Let's say we've got this continuous spectrum here, and it's just the section of the visible spectrum which our eyes can pick up, between 400 nanometers and 700 nanometers. And we want to look at the line spectra for hydrogen. So if we had a sample of pure hydrogen gas and we added energy into that particular sample, we would find not a continuous spectrum, but what's referred to as a line spectrum. So our line spectrum for hydrogen would look something like this. It's a discrete pattern of lines at particular wavelengths. And it's characteristic for hydrogen, so if we had an unknown sample of gas and we matched up its line spectrum with the hydrogen line spectrum, we could identify the elements. Now the Bohr model of an atom is used to explain the emission spectrum for hydrogen. The first thing that Bohr dealt with was the fact that energy is quantized. When we say that energy is quantized, that means that it only comes in discrete amounts. And we had an equation that dealt with that energy in our last section. Energy is in discrete amounts, which are whole number multiples of our Planck's constant times our frequency. Now, electrons move in circular fixed energy orbits. And we refer to the lowest energy state for electrons as the ground state for those electrons. And if we add energy in, the electrons move to what we call excited states, or states that are higher than the ground state. According to Bohr's model, only certain orbits were allowed, which means only certain energies are possible. These energies naturally lead to the explanation of the hydrogen atom spectrum. So let's look at this particular diagram. What we see is a change in energy along the y-axis of this particular diagram. And we see that if energy is added in, it's added in particular discrete amounts. So if we add in some energy, we're going to have a particular wavelength in the red part of our visible spectrum. If we added in more energy, we would have green, and if we added in even more energy, we would have a blue. So various energy levels must be found in a hydrogen atom, which show that when energy is added in, the electrons become excited into their excited state orbitals, and then as they fall back down to their ground state, they emit that energy at particular wavelengths. Now let's talk about a particular analogy. Let's say that we're standing at the bottom of a staircase and we're holding a tennis ball. And we add energy into that tennis ball by throwing it up the stairs. Well, that tennis ball is going to start to fall back down the stairs, and it may fall all the way back down to the bottom, or it may fall just partially down and stop on a step along the way. But the ball will never be found in between steps. That's kind of like what we look at when we talk about the Bohr model for an atom. The electrons absorb particular amounts of energy. They move to excited state energy levels, and then they fall back down to ground state energy levels. But the electrons can never be found in between those particular energy levels. When we calculate the energy of an electron, our equation is going to be E equals negative 2.178 times 10 to the minus 18 joules, that's a constant, times z squared over n squared, where n equals the energy level that the electron is in, And Z equals the nuclear charge for the particular atom. And we talk about this for a hydrogen atom, so our Z value will always be 1. Now, one thing in particular we want to look at in this particular equation is the fact that we've got a negative sign in front of our constant. And what that negative sign means is that the energy of an electron bound to the nucleus is lower than it would be if the electron were away from the nucleus. So in other words, energy has to be added in order for electrons to move farther and farther away from the nucleus. And energy is given off or emitted as electrons fall back down closer to the nucleus to their ground state. Now, if n equals infinity, that means the number in the denominator is a very, very big number. And the bigger the number gets, the smaller this value would get, until eventually there's no interaction between the nucleus and the electron. And energy would then equal 0. So here's a question we want to deal with. Calculate the energy required to excite the hydrogen electron from level n equals 1 to n equals 2. Also, calculate the wavelength of light that must be absorbed by a hydrogen atom in its ground state to reach this excited state. So what this means is we have the hydrogen electron in the first energy level. We have to add energy in order to move it from the first to the second energy level. So we want to find out how much energy the electron has in the first energy level, how much energy it has in the second energy level, and the difference between the two will tell us the amount of energy that had to be absorbed in order to move that electron from n equals 1 to n equals 2. And then once we calculate the energy, we can go through and calculate the frequency and then calculate the wavelength. So let's start with energy level 1. Okay, we've got our equation. We're going to plug in 1 for Z, and we're going to plug in 1 for N. And that's going to give us negative 2.178 times 10 to the minus 18 joules. That's how much energy we have for that particular electron in the first energy level. Now we're going to do the same thing for the second energy level. We're going to substitute in 1 for Z, because again we're talking about just one electron. And we're going to plug in 2 for N, because we're going to move to the second energy level. And that's going to give us a negative 5.445 times 10 to the minus 19 joules. Now when we think about that, that's a smaller number than 10 to the minus 18. So we're going to take those values, and we're going to take the less negative value and subtract it from the more negative value. And that's going to give us a delta H of positive 1.633 times 10 to the minus 18 joules. So that's how much energy would have to be added in order to move a hydrogen electron from the first energy level to the second energy level. It also would be equal to the amount of energy that would be given off if that electron were to go from the second energy level, where it's at its excited state, back down to the first energy level at its ground state. So the next thing we want to do is we want to calculate the frequency. So we'll take our Planck's constant equation, energy equals Planck's constant times frequency. We'll plug in the energy change that we calculated. We'll plug in our Planck's constant value, and we'll solve for frequency. And we're going to get 2.46 times 10 to the 15th reciprocal seconds. And then from there, we can use our speed of light equation and solve for the wavelength. So we'll plug in 3.00 times 10 to the 8th meters per second. We'll divide it by our frequency, which is 2.46 times 10 to the 15th. Our seconds will cancel out. We'll be left with meters, and that would give us our frequency. So we would get 1.216 times 10 to the minus 7 meters, or 121.6 nanometers. Now, if we look at that particular number, that number is less than our visible spectrum. Okay? So that means that it's got a lower wavelength than the visible spectrum, so it's got a higher frequency than the visible spectrum, so it's got a higher energy than our visible spectrum. So that means that our visible spectrum has a lower energy, which means the visible spectrum would not give enough energy in order to move that hydrogen electron from energy level 1 to energy level 2. The last thing we want to talk about is the Heisenberg uncertainty principle. And basically, there's a limitation to how precisely we can know the position and the momentum of a particle at a particular given time. Now, we've got an equation that deals with our Heisenberg uncertainty principle, although you're never going to be asked to calculate it. We want to look at it, though. Over on the right-hand side, we have h, which is our Planck's constant. We're dividing it by 4, and we're dividing it by pi, which is also a constant. That means that the value over on the right-hand side overall is a constant. That means that our uncertainty in position and our uncertainty in momentum over on the left-hand side must be inversely related. So the better we know a particle's position, the less accurately we know its momentum. Now, this limitation is very small for large particles, so you don't deal with it so much in physics, but it's much more important when you talk about very small particles like electrons.